right, welcome to section 5.2, where we are going to build upon the knowledge that we learned in section 5.1 on Riemann sums. And so these were ways that we could use to approximate the area of a region bounded by the curve in the x-axis on an interval. That was defined as a non-negative region, where it was always in the positive for what we saw. But what if a graph falls below the x-axis? How can we find the area of that? Well, we can using a Riemann sums. The difference is that the area is now not going to be positive. It is going to be negative, okay? So you kind of have to, that's why it's important to have that picture as to what we have. Now, what we were going to refer to this as is the net area. Because obviously if one's positive, one's negative, there's going to be some things that cancel out, and your answer could be positive, your answer could be negative. And we'll talk about that in just a second. So let's look at this first function, 1 minus x squared, and we're going to use a left Riemann sum in order to approximate the area from 0 to 3 given n equaling 6 subintervals. So what would be our delta x? How far from 0 do I need to go to get my next interval? Well, I'm going to do 3 minus 0, b minus a over n, which is 1/2. That means that for every half, I'm going to have a new rectangle. Okay, so I'm going to draw a graph here. 1 minus x squared, it's a parabola that's reflected over the y-axis but moved up 1. So if you need help getting that graph, that's fine. Over 1 and down 1, I would have as, actually, let me undo that. I'm going to put 1, 2, 3, kind of widen out my intervals. You're actually going to, if you were to have that pattern of a parabola over 1 and down 1, you're actually going to go through there at x equaling 1. Okay, so there's my graph. My parabola would end up going somewhere, like this on through. Okay, we're going to create our rectangles now using our subintervals, and that means that I need a rectangle at every half. So if I start at 0, I'm going to go a half. I'm going to get 1 at 1, 1 at 1.5, 1 at 2, 1 at 2.5, and 1 at 3. So a left Riemann sum. Let's remind ourselves what that means. On the interval from 0 to 1/2, I need the left-hand endpoint to create that rectangle to find the area or approximate the area of this curve. On the interval from 1/2 to 1, we're going to use 1/2, find its function value, which is right here, create that rectangle for the area to be approximated. Now here's where it's tricky when you have one that crosses the x-axis. Here's the function value for that. When I create it with the x-axis, there's nowhere for it to go. So there's really not any area that's going to come about by this little piece right here. It's just a straight line, okay? From the interval from 1.5 to 2, where's the function value? It is now below the x-axis, but I still want to approximate the area of that curve by just what's bounded between the curve and the x-axis. That's why my rectangle is going to look like that. On 2 to 2.5, I'm going to choose 2 as the left-hand endpoint. Come down. It's on my function. I'm going to create the rectangle with the x-axis there. Makes you feel better just to see all of them in blue. And then at 2.5, I'm going to come down here. I'm going to create that rectangle that I have. So our grid points here are going to be 0.5 or 1/2, 1, 1.5, 2, and 2.5. We are not going to use 3 this time. So we are going to use this to find our approximation. So I'm going to bring in kind of our summation notation a little bit, where I'm going to sum from k equaling, we're going to start at 1, and I need 1, 2, 3, 4, 5, 6. So I need 6 values of my function value at x of k times delta x. And that's what we were adding up all in last section. Was that function value is the height, the delta x is my width of the rectangle. We're multiplying those so that we can find the area of that rectangle. Now at this point, I'm going to put in what delta x is. I found out what delta x is. It's a half. So you can write a half, you can write 1.5, or not 1.5, 0.5 if you want. But this is just a constant. So at the end of our lesson in section 1, we knew that for a summation notation, any constant could be dragged out front. So I'm going to do that. And that is basically, in a sense, you're factoring out that 1/2. So I have 1/2, and now I need to sum up all my function values. Okay? Well, what values am I starting with? I'm starting with the left-hand endpoint at x equaling 0. So I need to know what f of 0 is. I then go to the next grid point, which is at 0.5. So I need f of 0.5. I need f of 1. And remember, we're doing this all the way until I get to 2.5. So f of 1.5, f of 2, and the last one is 2.5. Okay? Now, we can go and find these function values, and that's what we're going to do, and we can make use of our function, okay, 1 minus x squared in order to do that. So, notice that there are some areas that are above the x-axis and some areas that are below the x-axis. And so, the ones above are going to be positive, the ones below are going to be negative. So, that's going to come through when you plug in your function value. It's going to kick out a negative number for you. So, you're just going to realize that that's what that means. So, if I plug in 0 into my function, 1 minus 0 squared is 1. If I plug in 1/2, 1/2 will yield a 3/4 or a 0.75. What happens when I plug 1 in? 1 squared is 1, 1 minus 1 is 0, and that's this rectangle that doesn't contribute any area to that function. When I end up plugging in 1.5, I get a negative 1.25. When I plug in 2, I get a negative 3. And when I plug in 2.5, you get a negative 5.25. And those are my values evaluating the function at all those grid points. Now, use your calculator to bring all this together, multiply it by 1/2, and your answer for the area under that curve is negative 3.875. Now, does that make sense? Well, where is more of the area? More of the area is down here. So it's telling me that the net area between the difference between the positive and the negative is negative 3.875, okay? Now, I know that that's not the actual area of everything underneath the curve, but that's not what we're finding right now. We're just finding the net area by accounting for negative area and positive area. And so it should make sense because it looks, according to my picture, that there is more area in the negative than there is in the positive. So let's define what net area is. I'm going to consider some region R that's bounded by the graph of a continuous function f and the x-axis between x equaling a and x equaling b. The net area of R is the sum of all the areas of the parts of R that lie above the x-axis minus the sum of all the areas of the parts of R that lie below the x-axis. So we're summing the ones on the top, summing the ones on the bottom, and subtracting them. That kind of holds true to when I have these negative values here as well. Okay? So this kind of leads us into the idea of a definite integral. Okay? A Riemann or Riemann sums only give approximations to areas under curves. How can we use calculus to get the exact answer or the exact area for that problem? Okay? So we're going to use the idea of a limit. What is needed is for the number of subintervals that we have to go to infinity, and the width of those intervals then will go to 0. Okay? They won't equal 0. They are limiting to 0. AKA, we want n to go to infinity, the number of rectangles, and we want delta x to go to 0. That's the width of our rectangles there. So here's some illustrations, and in section 1 I kind of showed you an interactive tool that kind of showed you this along the way, that as our subintervals increase, in this case from 6 to 40 to 75, we ended up getting very, very close to the area. See, you have some overhang here, you have a lot of overhang and some missing stuff here. But as I let the number of rectangles go to infinity, which means then that the distance of those rectangles, the width of those rectangles goes to 0 and is very, very minute, this is where we get the idea of the net area under the curve. Okay? If it's all positive above the x-axis, you're going to get the actual area under the curve. Here we have to account for the stuff that's below there. Now, integral partitions do not necessarily have to be equal. When we work with these, we had delta x being the same thing, but it doesn't have to be that way, okay? It just makes it easier if those partitions are of equal length. Hence, that is what we are going to refer to as a general Riemann sum when you have partitions that are allowed to be of different widths. We're not going to get too much into that because it's, like I said, it's easier than if we just assume that our delta x's are the same length. So, this is another defining moment in calculus right here where we talk about the definite integral and giving us the area under the curve. And in this case, we're just kind of starting with the net areas. We'll talk about the actual area if we have some negative regions here in a little bit. All right, so we're going to say that a function f is defined on AB is integrable. It's a funky little term that says you're able to integrate it on AB if the limit as delta goes to 0, and we don't really have an x here, we're just saying that the partition is going to 0 of the sum of k equaling 1 to n of f of x sub k times delta x sub k. And that should look familiar to you. That summation is the width times the length of all those rectangles that we're adding up, but we're saying here that our partitions are going to go to 0. The lengths of each one of those rectangles is going to go to 0. Now, if that exists and is a unique over all partitions on AB and all choices of x sub k, all of our k grid points, this limit is what we refer to as the definite integral of f from A to B. And the way that we're going to write that is we're going to bring back that integral symbol from section 4.9 from A to B of f of x dx is equal to this limit as my partitions go to 0 of the sum of k equaling 1 to n of f of x sub k times delta x sub k. Again, this is the idea, the foundation, that it's the width times the length of the rectangles, creating the area, adding up all those areas, getting very, very, very small rectangles width so that I can approximate and get an exact answer to the area under the curve. So, just for some notation purposes, I'll change color so you can see this. The integral from A to B of f of x dx. We talked about this being the variable of integration in section 4.9. We talked about this being what's referred to as the integrand. We now can add on that this is our lower limit, and this is our upper limit. Just kind of like it was with our sigma notations. And that's what we refer to those as. Okay? All right, now remember that the variable of integration that we're working with is technically, most of the time, a dummy variable that is completely internal to the integral. Now, it does not matter what variable of integration is called, as long as it does not conflict with other variables that you're working with. So once you get into multivariable calculus, as long as they're kind of separate, then you're good. But they are just considered some dummy variables. All right, so let's take one of these limits and kind of break that down into equivalency of an integral notation. So we're going to assume that this limit is the limit of a Riemann sum for a function on this interval from 1 to 3. Hence, this is my A and that's my B. We want to identify the function and express that limit as a definite integral. Okay? Well, remember, this is f of x sub k. times my delta x sub k. So the function is going to come from here. Now, if I just want to know what f of x is, that means I can just rename my variables, take out an x sub k and put in an x. So I'm going to extract that just from what's inside these parentheses here and say that my function here is the 3x squared plus 2x plus 1. That's the function that I have. And can I now put that into my integral notation with my a and b on my interval to express this Riemann sum as a definite integral? Absolutely, we can do that, okay? Now, we can do this because this is a polynomial, and a polynomial is going to be continuous and integrable everywhere. Polynomials are so nice because there's really not too many problems that come along with it, okay? So the integral that I'm going to create has to go from a to b, so from 1 to 3 of this function of 3x squared plus 2x plus 1, and remember this dx is just kind of a notation thing so that we know what variable of integration that we are working with, okay? Now, what does this definite integral represent geometrically? Now, if you were to graph this function from 1 to 3, this is a parabola, okay? You're going to end up having something in the positive direction, okay? From 1 to 3, there's going to be some positive. So if I want to find the area under the curve, I'm going to actually end up having all of that area above the x-axis. So actually, this is not just the net area, it is the actual area of that curve, under the curve for that. So, what does a definite integral mean? It is the area, not net area, under the curve, bounded by f and the x-axis, okay? Now, you may want to make note that it's the actual area, not the net area, because f is positive on 1 to 3, okay? There's nothing that changes from a positive down to a negative, which creates an idea that we kind of had up here, whoops, sorry, on the other page, when we had some positive areas and some negative areas, okay? All right, very good. So we're going to just start off with some familiar area formulas in order to find the area under curve. So these are going to be some real basic functions that I work with here. The first two being linear, and the second one, hopefully you recognize that as a semicircle. So I want to graph this first, okay? So leave you some room to work underneath, but we're going to graph it first. I need to go from 2 to 4. And I'm on the line 2x plus 3. So there's kind of two things that you can do. You can graph going up 3 and then going up 2 over 1, up 2 over 1, grabbing your points. But you can also plug 2 in. 2 times 2 is 4 plus 3 is 7. 6, 7. So I would be approximately here. You can go up 2 then and over 1, which would be here for x equaling 3. Up 2 and over 1, which would be approximately here for x equaling 4. So there's the function, and we don't need the whole thing. We just need it on the interval that we're looking at from 2 to 4. So this is at 7, this is at 9, and the other one's at 11. All right, so if I were to find the area under this curve that's bounded with the x-axis and that curve, I'm going to create this shape, okay? Now, you should, on these very basic ones, be able to figure out what is that shape. Well, that shape is a trapezoid. So, can I geometrically find the area of a trapezoid? Absolutely. No calculus is needed here, but the idea of this is getting us to those functions that are not straight on one side to create a trapezoid. They are curves, okay? And that's where we're going. So, what's the area of a trapezoid? Well, the area of a trapezoid, back in your days of geometry, you should remember that it is 1/2 of your height times the sum of the bases. And so, remember the bases are the parallel sides. The height is the distance between them. So for our problem, we want to do 1/2. The height from distance from 2 to 4 is 2. The function value for base 1, this is going to be the function value on my function at x equaling 2. When I plug 2 in, times it by 2 and add 3, we found that that was 7. And the function value when x equals 4 is over here at 11. And so, geometrically, we find that it has an area of 18. And we can do that when we are familiar with the function, okay, and the shapes that it's creating. What about this line, 2x minus 6? Well, I'm going to start off here. Again, we're going to go from 1 to 6. 1, 2, 3, 4, 5, 6. So you can start at 1 and go to 6. You can graph each of the points. You can start down at negative 6 and go up 2 and over 1. So that means I'm going to be starting at negative 4. If I plug 6 in there, 6 times 2 is 12 minus, that gives me a value of 6. So I'm just going to create the kind of the 2 endpoints. Up 2 over 1, up 2 over 1. So I'm going to be going here at this 0 of x equaling 3. And so here is my curve, 2x minus 6. But notice that part of it's negative, part of it's positive. And again, we're just binding the regions between the curve and the x-axis. So I need this part, and coming perpendicular down here, I need this part. Well, if I was straighter, we could realize that that is basically made up of 2 triangles. And so to find the area, or in this case, the net area, which is the definite integral of this problem, that means I need to find the area of triangle 1 and add it to the area of triangle 2. But what do we know about the area of triangle 1? It is below the x-axis, therefore that area is negative, and I need to account for that when I'm finding the definite integral, which is equivalent to the net area of the function with the x-axis. So, let's talk about this triangle right here. Area of a triangle is 1/2 base times height. So I'm going to count this as my base and this is my height. So my base here is 2. My height is 4. You can do 4 times 2 if you want and change the order. It doesn't matter. But then I have to add to that 1/2 of this base times this height. So this is 1, 2, 3. So 1/2 of 3 for my base. And this height we said was 6. So I'm multiplying that by 6. And so now finding these numbers gives me the net area or the definite integral for this function. 1/2 of 2 goes away and then we have a 4, so negative 4. This gives me 18. 1/2 of 18 is 9. Negative 4 plus 9 gives me a value for my definite integral of 5. So this is equal to 5, or it is geometrically the net area of that function from 1 to 6 with the x-axis. Okay. All right, the next one, I alluded to that this is actually a semicircle. So make sure that you know how to graph some of these functions when you're asked to do them geometrically. And so this is a semicircle that is centered at the origin with a radius of 3. This is square root of r squared minus x squared. So this is actually radius squared. The radius here is 3. So if I were to graph the positive version of that semicircle, then I have a radius 3. That means I basically just have that upper half. That's a really bad semicircle. I have the upper half of that semicircle. Maybe I can do a better job. That's a little better. And so notice that we're finding the definite integral from 0 to 3. But here I've graphed from negative 3 to positive 3. So from 0 to 3, the region that I'm talking about is just here. So we're looking at what is the area from x equaling 0 to x equaling 3 bounded by the graph, the x-axis. And so this, if I had the full circle, what part of that circle do I have? Well, I have 1/4 of it. So I need to find out what is the area of 1/4 of the circle. So area of a circle is pi r squared, if you don't remember that formula. And I'm going to throw the radius of 3 in here to find my answer. So I need 1/4 pi times 3 squared. And 3 squared is 9 times 1/4. I can just multiply the tops and get 9/4 pi as an exact answer for my problem. Okay? All right. Very good. So, again, working with some basic functions, Getting the idea of that definite integral as the net area of a function from a to b with the x-axis. Now, here again, we're kind of building our foundation still. Using the graph of f with the areas of the regions bounded by its graph and the x-axis is given, find the values of the following definite integrals, okay? So the area of this piece is 12, this is 10, but it's negative because it's underneath the x-axis. This is 8. So we now have to find the integral, the definite integral from a to b of f of x dx. This is all f of x. So what is the area under the curve of f from a to b? So from a to b, I'm talking about this area right here. This definite integral is 12. There's really no work to be done in this case, okay? From b to c, what is the area under the curve of f of x from b to c? That is bounded with the x-axis. And well, from b to c is this region right here. Notice that it is below the x-axis like I had already told you. Therefore, the definite integral is defined to be negative 10. All right, let's combine a couple of these. Now instead of going in just one region, what if I want to go from b to d? So I'm looking at this whole part of that function. I need to account for this area and for that area. So if I do that, take that off, then I have to again count for this to be negative. So I'm going to go from negative 10, add to that the area for this region, which is a positive 8. And then the net area here looks like it's negative 2. And then finally, I'm going to do the whole thing. We're going to go from A to D, so I need to sum each of these areas, making sure I do negative for the 10. So I get 12 equals 12 minus 10 plus the 8, which will give me a value of 10. So those are the definite integrals for this graph of f. But what if I throw some absolute value onto a function? We've talked about the definite integral being the net area of the function if part of it's above and part of it's below. It is the actual area if all of it's above or all of it's below. But what if I do the absolute value of that function? That means that everything has to be positive if it's under absolute value. So this definite integral will be defined to be the sum of all positive areas of each region. So what would that look like? If I were to change this up, and if I do the absolute value of x, that means that everything down here in this negative has to be up here. It would just change it positive. So basically, I end up getting that piece that comes up here. And I would have a positive region there now. So the answer to this integral would now be the sum of all the positive regions, which is 12, 10, and 8. Adding all those together would give you an answer of 30. So that is the actual area of this region. This is the net area from A to B of that region, or A to D, excuse me. So make sure that you're very, very careful, okay? If a problem asks you for the actual area, you got to make sure all your regions are positive within that, okay? So let's turn to some properties of definite integrals, use those here on some of these examples. Then we'll remind ourselves of some Riemann sums and then do an exact area. Our first exact area, which is a long one, I will tell you, but it was, again, foundation to what we need to come in section 3. All right, so we're going to let f and g be integrable functions on the interval that contains a, b, and p. So I'm going to talk about the integral from a to a of f of x dx. Now this is just a definition that I have, but it should make sense. Go back up to this graph. If I want to go from a to a, what should be the area under the curve if I start at a point and I end at that same point? Well, there is no area. There's nothing there to account for the area under the curve. So that is defined to be 0. Any integral from a point to itself of any function is going to be 0. Another definition that I have, that if I start from b to a, now our interval here is going from a to b, where p is in the middle. Okay, we're going to define p here in a minute. But if I start from b to a, from the higher to the lower of my function value dx, by definition, we can turn that around to go from lower to higher again of that function, which is what we like to see, but I can negate that. That is equivalent, and that again is just a definition. Now the other properties can actually be proven. Again, in a higher math class, you may have to prove some of these things in advanced calc or whatever, but here we are not. I'm just going to give them to you. So the integral from a to b of the sum of two functions, just like when we were working with our summation notation in the last section, we can separate that and we can separate the integrals here. So I'm going to do f of x dx, add to that the integral from a to b of g of x dx. And again, don't be lazy like with limits. We didn't want to drop our limit symbol. With integrals, you don't want to drop your dx's. Those are important. It is just a notation thing, but it is important to keep. Now, the sum works and also the difference works. So you may want to put a plus or minus there because it is true that you can separate with a plus and with a minus. All right, next one, from a to b of c times f of x dx. So I have a constant that is timesing by a function. Same with sigma notation, same with limits and all that kind of stuff. We can take that c out front and then do the integral of a to b of f of x dx. And our last one includes p, okay? P is a number that's between a and b. So if I have an interval, starts at a and ends at b, then p is somewhere in between here, okay? Just so that you know. So the integral from a to b of f of x dx for this property says that if I have some subintervals here, I can do the area under this curve from a to p and add it to the area under this curve from p to b, and I get my total area from a to b. It's almost like segment addition when you're working in geometry or angle addition, but this is, we can call it as integral addition. A to p of f of x dx, add that to p to b of f of x dx. And so that's basically breaking up your sums. And sometimes you have to do that depending on the type of problem that you have. And our last one is the integral from a to b of the absolute value of f of x dx. And this is just my reminder that this is the sum of all positive areas. Okay, so make sure that whenever you have the absolute value of a function that you are adding up all of the positive areas for that function. Okay, and that's one that you might have to split up, being able to take the integral of to have them positive. All right, very good. Let's try these. Generically giving you a function f of x, two integrals that go from 0 to 5 equals 3, and the area under the curve from 0 to 7 is negative 10. So what that tells me is that the area from 0 to 5 is positive, but the total area, when I include 5 to 7 here, drops to negative. So that means that from 5 to 7 it is a function that is down underneath the x-axis, and a lot of it, in order for the net area here to now be negative 10 from a net area of 3. All right, so let's look at 0 to 7 of 2 times f of x dx. Now notice we're going to use our properties. Let me scroll back up a little bit. I have a constant times a function. By this property right here, that constant can be pulled out front. So that means I can take 2 times the integral from 0 to 7 of f of x dx. And your strategy here is to try to figure out how you can get this by itself, how to get this by itself, so you can plug in the negative 10 and the 3. So I've done that. I can now exchange this integral from 0 to 7 of f of x using one of my properties, bringing out that 2, and I can replace this whole thing with what it's equal to of negative 10, and my final answer here for this definite integral would be negative 20. Let's do the same thing on this one, but notice here the lower limit is at the top and the higher, or the bigger number, is at the bottom. Normally we want to see that reverse. Well, we had a property that reverses those limits, and that is this one right here, which means that if I want to reverse those limits, I have to make it negative. Now notice we also have a 6 hanging out here, so I'm going to kind of do 2 steps in one. I'm going to pull the 6 out. I'm going to switch my integrands from 0 to 7 so I can match what I have here, but that now needs to make that 6 a negative 6 of f of x dx here. Okay? So, again, I did that in 2 steps. I switched the integrands, made it negative, and I pulled the 6 out front. And then now I can exchange the 0 to 7 for the negative 10 and get a final answer of 60. Now I'm kind of doing a circle here. Let's go to this one and we'll end with 5 to 7. So if I have the integral from 5 to 5 of f of x, that means I want the area under the curve from x equaling 5 to x equaling 5. That we have a definition that is 0. Can't go from one point to itself with having any area whatsoever. All right, now I need to find the integral from 5 to 7, but notice I'm only given 0 to 5 and I'm given 0 to 7. This one we have to think a little bit more. Here I want to kind of just bring it down to a number line type thing. If I'm going to 0 to 7 and from 0 to 5, I have this area under the curve, which is 3. I have this area, which is negative 10. I'm looking for this area, okay? So, just like segment addition in geometry, what do I have to do to this large number and this small number to get this other small number? Well, let me ask it this way. If I had the two smallers, I would take this plus this to give me that, which is this guy right here. But if I have the larger that's given to me and a smaller that's given to me, then I can take the larger minus the smaller to equal that interval from 5 to 7. So I'm going to write that out for you. We're going to go from 0 to 7 of f of x dx, and I'm going to subtract the smaller interval from 0 to 5 of f of x dx in order to receive the interval from 5 to 7. So this value is negative 10, that I want to subtract that value, which is 3, to give me a definite integral value of negative 13. And that would be our answer there. Okay, so you're going to have quite a few of these to kind of work with those properties to be able to figure out what the answer is of a definite integral, because we've not yet figured out how to do that. That's to come here in section 3. All right, now I wanted to revisit this idea for you using a Riemann sum, just so you don't get out of sync with that. I did it as our first example here in section 2, but I also wanted to kind of show that to you in this sense, where they're asking for the approximate net area bounded by the graph of f and the x-axis on the interval using a left, a right, and a midpoint Riemann sum. Now, the good thing is here I'm only going to need 4 values, and my interval is from 0 to 4. So if we think about delta x, I go 4 minus 0, b minus a over n. So that means that at every integer, I'm going to have a new rectangle, okay? So I'm going to go ahead and kind of start by plotting this function. So from 0 to 4, at 0 we're at 2, and because it is linear, I go down 2 and over 1, I can go down 2 and over 1, down 2 and over 1, down 2 and over 1. And that is my function. Now notice that if I'm gonna bind that with the x-axis, that means I'm looking at this area and I'm looking at this area, but there are some of those that are going to be negative, so please make sure that you remember that. All right, so let's talk about the left Riemann sum. To approximate the area for this function from 0 to 4, I'm going to write it in our definite integral notation. From 0 to 4 of 2 minus 2x dx. I'm going to use a Riemann sum to do this approximation. Now remember, with the Riemann sum, I had to create all of those rectangles. So I'm just going to draw on my picture the left one. And so remember, at x equaling 0, I'm going to create that rectangle. At x equaling 1, on a left endpoint, there's no rectangle that happens there. At x equaling 2, there's my function value, so there's my rectangle. X equaling 3, there's my rectangle that I'm going to approximate. So notice we're using x equaling 0, 1, 2, and 3. We're not using 4 here because it's a left Riemann sum. So the width of each of those rectangles, my delta x that I can factor out front, is a 1. Then I need to find the heights of each one of those rectangles, which is finding the function value at each of those grid points. So I'm going to take 1. If I put 0 in, I get 1, I get 2. Then when I put 1 in, I get 0. Then I get negative 2 and negative 4. So, should the area be positive? Should it be negative? I'm hoping it's going to give us a negative number because it looks like more is in the bottom than it is in the top. So, these are going to cancel. This is going to end up with negative 4 times 1, which gives me negative 4. If I want the right Riemann sum, as they are asking for me, so I still have the same integral notation, we are just calculating it with the right Riemann sum this time. Now, with the right Riemann sum, it would change here. Let me change a different color. A right Riemann sum would be at 1. There's my first rectangle. Here's my second rectangle. Here's my third rectangle. And here would be my fourth rectangle. Okay? So it looks like we even get all negative numbers here for areas because we get a 0 for this first one. So let's do that with... We're starting at 1, going to 2, 3, and 4. So I need the function value at 1, function value at 2, function value at 3, and the function value at 4. And so when I find these values, you can steal from some of them up here. We get 0, negative 2, negative 4, and the pattern would mean the next one would be negative 6. And you can confirm that with your calculator. This would give me a definite integral of negative 12. So I have a wide difference here, negative 4 and negative 12. We know that the area is somewhere in between. This one's going to be smaller, this one's going to be over. And so the midpoint, if you recall, is the one that is the most accurate, 0 to 4, 2 minus 2x dx. And I'm going to do this without drawing any rectangles of midpoints because we're going to adjust to finding the midpoints of these intervals, which is at 1/2, 1.5, 2.5, and 3.5. So I need my width and my function values at all the halves, which are all the midpoints. Okay, and I will tell you, and again, you can plug these into your calculator. This is 1 plus a negative 1 plus a negative 3 plus a negative 5. So the ones are going to cancel themselves out. Negative 3 minus 5 is a negative 8. So that again, each one of those are 3 approximations to the area under the curve that is bounded with that curve and the x-axis. So again, good way to remember those Riemann sums and linking it with now our definite integrals. Okay? All right, very good. And here comes the culmination of this section, kind of the culmination which gets us to our exact area for our definite integral. So, we know that if f is integrable on AB, then the integral from a to b of f of x dx is equal to the limit as our partials go to 0 of the summation of k equaling 1 to n of f of x sub k times delta x sub k. And again, this is just that general definition of that Riemann sum. For any partition of AB and any points x sub k, if that is true. All right, to simplify these calculations, we use those equal space grid points and right Riemann sums or left Riemann sums or midpoints. We're going to kind of defer to the right Riemann sum here for each value of n. And so we let, remember, delta x sub k, which is going to be the same as delta x, be b minus a over n. That's going to be important. And to find our grid point using the right Riemann sum, then x sub k is going to be found by taking your starting value and adding to that k times delta x, where k is equal to our positive integers up to n. Then the idea is once we know what that is, we're going to take the limit as n goes to infinity. The number of rectangles that we have is going to be infinite. And once we take that limit as n goes to infinity, that's going to lock in our exact area for our function, okay? That's what we want. So here's the notation. We want the limit as n goes to infinity of that summation. So I want the summation of k equaling 1 to n, so I'm changing it basically from my partitions now in terms of n, of f of x sub k times delta x. Okay, so this is what we're going to be finding in this problem. And I will tell you, I'm kind of doing a more difficult one because I'm starting somewhere other than 0. We're starting at 1 to 4 of this quadratic function. If you start with 0, that's way so much nicer, but I'm not going to show you a more difficult problem, okay? All right, so here is A, here is B, and we have this function of x squared minus 4. Now, if I do x squared minus 4x equal to 0, factor out an x to find out where that crosses the x-axis, it's going to be at 0 and at 1, 2, 3, 4. So I have a parabola here that's going to be crossing, but I only want it from 1 to 4. So I can kind of dash here. When I get to 1, if I plug 1 in there, I get negative 3. Then at negative 4, I'm going to bottom out and come back up. Okay, actually I should dash that too, because I'm not looking within that. Past 4 on my interval. So here's from 1 to 4. So the area that's in question is this little piece right here. So again, it's really, really important to make sure that you graph that function first, okay? All right, so let's first, what I want you to first do is to figure out what delta x is. That's by taking b minus a all over n, and so this time we don't know what n is. We're just letting it be generic because eventually we're going to let n go to infinity. So next thing you want to do is to find your grid points, x sub k, okay? X sub k, I told you right here with the right-hand endpoint is 1 plus k delta x. So I want my a value to be 1. K is going to be changing always, that's our variable, times delta x, which we found to be 3 over n. Okay, so I'm going to simplify that. And I'm going to be able to use this to evaluate my function. Okay, so x sub k here is going to be 1 plus, I'm going to multiply k times 3 and get 3k over n, just to make it as simplified. Okay, so I need this, and I need this to be able to find the summation of k equaling 1 to n of my function value at x sub k times delta x. Okay, now we are going to start this. Now, for the time being, I'm going to drop this off. I'm not even going to worry about that. I'm just going to worry about k equaling 1 to n of f of x sub k times delta x. And that's, again, where I want to start. Now, I'm going to plug in what I found for x sub k and for delta x into here. So I get the sum of equal 1 to n of f of 1 plus 3k over n times delta x was 3 over n. Now we have to remind ourselves, n is just a number. We're going to let it go to infinity, so 3 over n is just a number as well. What's changing here is my variable k. So if that's just a number, I'm going to choose to bring that that constant out front, and I'm going to say that this is 3 over n times the summation of k equaling 1 to n, and now's the time I'm going to evaluate this function value at my x sub k. So this is where I need to take this and plug it into my f function. So I'm going to take this and I'm going to plug it in wherever I see an x into my function. Okay? So I need to take 1 plus 3k over n and square it. That's what my function tells me to do. Minus 4 times that same value. 4 times 1 plus 3k over n. And that is evaluating my function there at 1 plus 3k over n, which is your x sub k. All right, now that's a lot of where the calculus starts. Here comes a whole bunch of algebra. Okay, so stay with me on that. The first thing I'm going to do is FOIL this. Write this out twice and FOIL if you have to, or if you know the pattern, by all means, do the pattern. That's what I like to do, okay? So the pattern of a quantity squared is you square the first to get 1. We multiply these and double. So 1 times this is 3k over n. Double 3k over n gives me a 6k over n. And then I'm going to square the last, and I have to square all pieces. So I get 9k squared over n squared. Then I'm going to distribute my 4. So I'm going to get a minus 4 minus a 12k over n. Okay? Now, you don't have to simplify at this point, but I always like to just so that I can kind of keep things concise. I've seen people where they go directly into their summations, distributing of that. But I'm going to simplify one more time. I still have my 3 over n. Don't forget about that out front. K equaling 1 to n. I'm going to start with my k squared first. So I'm going to get 9k squared. And actually, well, okay. I'm going to keep it like this. Over n squared. I'm going to combine these two fractions. And notice I have a 9 instead of an n. Sorry, that should be a 6k over n. I think I said n, but I must have written 9. 6k over n minus 12k over n. There's a common denominator, so I get a minus 6k over n. You want to be very meticulous on these types of problems because there's a lot of places you can make a mistake. Then I'm going to combine my constants. 1 minus 4 gives me a negative 3. So that's my conciseness. Now, what we can do with our summation and what we learned at the end of section 1 was that I could distribute those summations into each one of those. So I'm going to do that, 3 over n. So what I get, now, I'm going to extract all these pieces off. Remember, these are just constants. So I'm going to leave the k squared and the k with the sigma, but I'm going to take out everything else. So I get sigma of k equaling 1 to n of k squared. Pull this constant of 6 over n out front of this sigma that I'm distributing in of k, minus, bring that sigma over here with that constant. We had a property that just talked about having a constant, and so that's me distributing those as well. Now, speaking of a constant with your sigma properties, these are the properties that I'm talking about that you probably want to remember. The sigma notation of k equaling 1 to n of that constant. Remember, I can take that constant times n. And here, what do I have? I have a k term and I have a k squared term. So I want you to remember the k term was n times n plus 1 all over 2. This is why we practiced it last time, but we were having exact numbers and not just n's. And of k squared, that was n times n plus 1 times 2n plus 1 all over 6. So these things are going to come into play right now into our problem, okay? So I'm going to replace this with this expression. I'm going to replace this with this expression. And I'm going to go ahead and multiply these two things together because that's what my sigma properties allows me to do. So I get 9 over n squared times n plus 1 times 2n plus 1 all over 6 minus, I have my 6 over n here, and I'm going to replace this sigma of k equaling 1 to n of k with what it's equivalent to here of n times n plus 1 all over 2. Again, be very meticulous here. And this property with a constant tells me I can just multiply 3 times n and be done with it. Okay? All right. Again, algebra, algebra, algebra. Make sure that you can simplify here pretty nicely. So I'm going to simplify this into 9 and leave me with a 3 and a 2. I can cancel this in with that in. And I'm going to go ahead and FOIL this piece out as a 2n squared plus a 3n plus a 1. And I just FOILed that. That's all I did there with that. Okay? All right. So I'm going to take 3, 2, and n. So I'm going to have 3 over 2n. Then I have 2n squared plus 3n plus 1. Simplified for just this first term right here. Okay? Now let's simplify this term. Well, first off, the n's are going to cancel. The 2 is going to go into 6 3 times, so I get minus 3 times an n plus 1. And then I have a minus 3n also in the end. So again, take it in baby steps. Don't do too much at once. All right, now here's where lots of options come into play. You can distribute this through. What I'm going to do is I'm going to distribute this 3 over n to here, and to here. Okay, so I'm going to multiply everything by 3 over n. I'm going to distribute that in now. So when I do that, I get 9 over 2n squared times my 2n squared plus 3n plus 1. Then I'm going to multiply 3 over n times 3, which gives me a minus 9 over n times an n plus 1. And then I'm going to multiply 3 over n times 3n. The n's are going to cancel, and 3 times 3 is 9. So that's where I'm at this point. I promise we're almost finished. This is a marathon problem, but it's a very, very good problem, again, to establish our foundation for our definite integrals, okay? And to do fundamental theorem of calculus in the next section to find the exact areas. All right, so now all I'm going to do is I'm going to distribute and distribute. So the 2n squares are going to cancel, so I'm left with 9. Then n's going to cancel with 1 down here. 9 times 3 is 27 over 2n. 1 times anything is itself, so 9 over 2n squared. Minus 9 over n times n is just 9. Distribute gives me a minus 9 over n. And I have my minus 9. Well, part of that's really nice because the 9's here are going to cancel out. And I'm just left with these 4 terms. Now, those 4 terms are all the way simplified. And so if you recall, that is what just the summation is equivalent to. When we started, it was that summation of k equaling 1 to n of that function value times delta x. But now, to finish the problem off, I've got to bring back in that limit as n goes to infinity. So I need to now take the limit as n goes to infinity of this 27 over 2n plus 9 over 2n squared minus 9 over n minus 9. And since that's what my expression is equivalent to. Okay, so going back to limits at infinity, if I had any number over infinity, remember that went to 0. So it's important for us to know those limits before we get to here. That's going to go to 0, that's going to go to 0, and that's going to go to 0 very beautifully. And what I'm left with is the limit of a constant, which is equivalent to that constant, aka the area under the curve for this function from 1 to 4 is negative 9. Now, should that be? Does it make sense that it's negative? Yes, it is below the x-axis. So therefore, our area, our definite area, or our definite integral of our net area should be negative. Okay? All right, very good. So I know that was kind of a marathon section. I know section 1 and section 2 here of chapter 5 have been pretty lengthy. So make sure that you understand what we're doing within these sections because it's so important to not only the foundation of the integral part of calculus, but also of what's to come in Calc 2 and Calc 3 as well. All right, until next time.